Hi and welcome to this tutorial on transformers. The focus for this is to explain in detail how transformers work and to use Faraday's law and Lenz's law to develop this common formula. Just briefly, here's a picture of a transformer with the primary coil, the supply, secondary coil and iron core. We're not going to go into the applications of transformers in terms of like mobile phone chargers or distribution of power. This is really about the details if you're interested in learning more about transformers, the actual physics. So let's start out. I'm going to show you an animation. It's going to start with this primary coil, including the supply voltage. It'll then introduce the iron core and then the secondary coil as well. So here's our primary coil with our supply voltage. It's an alternating supply, so the current will move left to right and then right to left. Let's watch a short animation. The current moves left to right, it increases, then decreases, stops briefly, then the current increases, decreases, stops briefly, turns around. You'll notice that a magnetic field is created due to this current flow through this coil, or solenoid we can say. We'll use the word coil mostly for this tutorial. So through the primary coil, you'll notice that these arrows increase, as do the letters, as the magnetic field increases, and they decrease in size with the strength of the field too. Now the direction of the magnetic field can be determined using the right-hand solenoid rule. So we use our fingers to curl in the direction of the current, and our thumb points in the direction of the magnetic field, so away from north or towards south. So you could consider the thumb also being the north pole of an electromagnet. Okay, so field direction, the current now switches direction, and so fingers still curl in the direction of the current, so from right to left, and thumbs pointing down this time, so the magnetic field points downwards. However, the field is constantly changing, and that's what can cause an induced current in the secondary coil. So let's introduce the iron core now. There's some other things going on in the iron core that we'll explain later, but basically the magnetic field generated in this primary coil will also affect all the tiny magnetic domains of this iron core, because iron, of course, is a ferromagnetic material, which means its little magnetic domains can align with an external magnetic field, in this case caused by this electromagnet. So the magnetic field from this primary coil will be aligned with all the domains of the iron core, and therefore will be directed around the entire coil. Entire core. Okay, around clockwise, including the important part through this secondary coil. So let's have a look at the secondary coil now. Well, first we can see the changing magnetic field within the whole entire iron core, including this important section. And now we'll introduce Lenz's law. Lenz's law says, well, it's said in a lot of different ways, but the way I like to think about Lenz's law is that whenever there's a changing magnetic field, there will always be an induced magnetic field to oppose the changing magnetic field. Now, the word induce just means to cause, be caused by. So, there's a magnetic field caused by the changing magnetic field through this secondary coil. Here we go. So as the current goes from left to right, we can see an increasing magnetic field going down. So what's the opposite of an increasing magnetic field? We need to reduce it. How do you reduce an increasing magnetic field? Do the opposite. So the magnetic field's pointing down, but because it's getting bigger, we'll oppose it by having an induced magnetic field pointing upwards. Okay. As a consequence of that, we have an induced current. So the current flows from left to right around that secondary coil. There's no battery here. This current is simply being induced from the fact there's an induced magnetic field. So that's while the magnetic field is growing. Now look at the magnetic field. It's reached its peak. It's about to decrease. So decreasing magnetic field. Decreasing magnetic field. What's the opposite? We need to increase it. So the induced magnetic field will point downwards because we had our downwards magnetic field decreasing. What's the opposite? Increase it back up. So let's get some induced downward magnetic field. So thumb pointing down, fingers curl from right to left. So the current's now flowing right to left. Amazing, isn't it? No battery, just all because of the induced magnetic field. So that's how a transformer works. Now, I skipped over something that we'll look more carefully at. I'm just going backwards. So inside the iron core, here we go. In the core itself, if we zoom in, we can actually see there's little tiny currents called eddy currents, E-double-D-Y. Now these currents are also induced currents, just like the current through the secondary loop, secondary coil. So the difference, I suppose, is that the charge carriers in this secondary coil are confined to the wire. The charge carriers in the iron core are just the part of the material itself. So technically it's electrons that are the charge carriers for metals, but we always use conventional current. So the electric field direction is positive to negative, so we assume positive charge carriers, even though that's not actually the case. But by convention, if this magnetic field is increasing to the right, Lenz's law says we'll oppose that, so we have an induced magnetic field to the left. Fingers curl in this perspective in an anti-clockwise direction, so there's the direction of the induced current in the core. Now the magnetic field is going to decrease, so therefore decreasing magnetic field, the induced field will go to the right to try to increase it again. And now this time we have our fingers curling clockwise. The eddy current goes clockwise. Now that's annoying for a transformer because we're trying to transfer energy from this primary coil to the secondary coil and then attach a load to it. If we lose all this energy from currents in the core, well, that's just wasted energy. Because of course, once you have a current flowing in this core, those charge carriers are colliding with the atoms in the material and energy is being transferred for the atoms as heat. So that's useless. So what we do instead, we laminate individual sheets, I suppose, of the core. So separate the core into sheets, cover them with some insulating material, so we call that laminating, and then put them back together. That way we still have all this beautiful iron that the magnetic domains of the iron can still align with the field that's being generated in the primary coil, but the difference is there's not a chance for many types of eddy currents to flow around in a circular fashion when there's all this insulating material between the strips now. So that's a great idea. And you can get transformers to be about 99% efficient by designing them well, and that's one of the good design features of modern transformers. Okay, so that's how they work. One more little point before we go into the formula. If we go back to the primary coil just by itself, it's clear there's an induced magnetic field due to the changing field inside this coil. But if you think about it, even though the field in this core is generated by this primary coil, there's still a changing magnetic field in this primary coil. Okay, check it out. So changing magnetic field, I know it's caused by the current in the coil, but nonetheless, there's a changing magnetic field in this coil. So therefore, I don't think I've got an animation for this. I might just have to take a little picture of it and pop it in here. So as this magnetic field is increasing, Lenz's law says we must oppose that. So it's going upwards and it's increasing. So the opposite is to go down to decrease it. Now, I'll do my best here to draw a hand. There's some fingernails. Oh, Mr. Finger. Anyway, hopefully you get what I mean. Thumb's pointing down to oppose this changing magnetic field. And fingers are actually curling from right to left. So the current is trying to go the opposite direction from what the supply voltage is causing it to do. So if it's going the opposite direction, opposite current, that must be an opposite voltage pushing that current in the opposite direction. So we call that a back voltage or back EMF. Okay? And so when we look at the transformer, that's why you have a voltage across this secondary coil, and that's clear because there's a current flowing. But there's also a voltage across this primary coil as well, which we call the back voltage. Now, you'll soon see the back voltage is basically the supply voltage. So I'll show you that now. So Faraday's law. It's in words here, but basically Faraday's law is this formula. This is the simplified version we often see in high school books, and it's, works really well for most questions you'd be asked. So the EMF or voltage equals negative n, so the number of turns in the coil, and as long as the turns are packed closely together, it's not so important for a transformer, I guess, because the magnetic field is sort of maintained within this core. But if we go without the core, see how the field actually leaks out to the side of the coil? It doesn't just go through it and out the ends, it leaks off to the side. So if you have the coils all close together, probably that field will be constant through the coil, the whole coil, all the turns. But it's an important point to note that they should be closely packed to make sure that we get the same field through all those turns. This letter is phi. It's a Greek symbol called phi. It's the flux, and it's the product of the magnetic field, B, and the area perpendicular to the field. And so in the transformer, then yes, the field is constantly changing. The area is not. So the area would be a circle. That's constant for both primary and secondary coil. So while the area is not changing, the magnetic field is. Therefore, the flux does change, and therefore you do get what we call an induced voltage, or induced EMF. Right, so why is the induced EMF the same as the battery voltage, basically? Well, it's because, and I'm going to draw a DC circuit because it's easier to think through than an AC circuit for now. If we have a coil, it seems like there's no resistance, but there actually is some resistance in the coil. We'll assume the connecting wires have no resistance, but I'm actually going to mentally separate the resistance of the coil with the other properties of the coil. Because remember, the coil can have an induced voltage across it that's not related to the resistance. That's the induced voltage. Resistive voltage drop is V equals IR. So they're totally different formulas, induced voltage versus voltage drop across a resistive load. Let's just say the supply was 10 volts at a particular time and the current happens to be going that direction. This, using a DC symbol, is appropriate if we're going to look at an AC circuit at one particular instance. Here's the resistance. Let's say it's a very small resistance and only has 0.1 volts lost across it. This would have 0 volts across it in terms of V equals IR, and the reason is the formal definition of Faraday's law is the closed loop integral of the electric field dot product with the small changes in length across the loop, okay, the closed loop, which is, you can start anywhere, but as long as you finish in the same spot. That's the definition of a closed loop. So if we look at that, that relates to this formula, voltage equals electric field times distance. So these are the voltages. So another way of saying it when this comes to a circuit, we can simplify this integral to the sum of all the voltages equals that. Now you might be thinking, hang on, the sum of the voltages in a closed loop is 0 according to Kirchhoff's voltage law, but that's just in a simple case where there's no coils. And that's usually what you start with when you're doing basic circuit analysis, is just resistive loads, no coils. So therefore Kirchhoff's law that the sum of the voltages in a closed loop is 0 is fine, but the law doesn't hold once you have coils in. Faraday's law holds for every scenario. Okay, so if we take this to be true, then the sum of the voltages, we don't include this one because it's not a resistive load here, it's a coil. This term, is over here. So we don't include this in our closed loop. And the reason, I suppose, we took the resistance out of this coil and we put it over here. So if this has no resistance, if resistance is 0, then V equals IR, V must be 0. And if V equals ED, if that's 0, and the distance is some actual value, a non-zero value, well, the E must be 0. So we can't include anything about the voltage here on the left side of the equation. This is all about E times D. So on the left side, we've got the sum of the voltages, and I might just go to a new page now. So we had our 10 volts, there's the current, 0.1 volts, and that's our coil, so it's not counted. And if we do the sum of the voltage equals negative N, all that, then we have the sum of the voltages. Well, there's a few conventions we can use for this, but we're going to start here and we're going to go around that way. Now if we look at the electric fields, positive, negative, that's negative, this is not included in these sum of the voltages. The direction of the field is that way, it's that way, positive to negative. As we go around, the electric fields in the opposite direction to the distance we're travelling, so therefore it's negative, so that'll be negative 10. This is in the same direction as the direction that we're travelling, so that's going to be plus 0.1, and that equals negative N. So all the stuff related to our primary coil. So now we can work out what the primary voltage is. It's negative 10 plus 0.1 is negative 9.9. Cancel the negatives. There we go. So that would be the primary voltage, 9.9. And like we explained before, that back EMF, that's going to be against the current direction. So it'd be kind of like, and this is not strictly true, but to imagine, it's kind of like having a battery that's pushing against this battery because it was a back EMF, remember? And we saw that in that previous diagram where the current is pushing against the current from the supply. There we go. And that battery is facing opposite directions. That's kind of what's happening here. Either way, there's a voltage across the primary that's 9.9. It's nearly the same as the supply. So we can say the supply is the primary. Okay? Now, how does that relate to the formula that we had in the first place? So the formula is voltage of the primary over the voltage of the secondary equals the number of turns in the primary over the number of turns in the secondary. So to develop that, we know the primary voltage is given by, and we'll put P for primary for all these things. We know the voltage for the secondary Okay, it's the magnetic flux of the secondary of the time for it to change. But when we look back at the diagram or the animation, we can see that that magnetic field through the primary is always the same as through the secondary. Therefore, since flux is the magnetic field strength or magnetic flux density times the area perpendicular to that field, we can see that the flux is the same for everybody, since the field is the same for everybody, primary or secondary. So if we say that the primary is the same as the secondary flux, then we no longer need to have secondary as a special thing. We can just call it the primary flux. Might just make that a bit nicer. Okay, and that can be primary as well, because the time taken is the same. Switches in direction at the same time as the primary and the secondary coil. So now if we do Vp on Vs, that equals Vp is negative Np, all that, over negative Ns and then you'll notice those two terms are the same, therefore cancel. The two negative signs can cancel, and we're left with Vp on Vs equals Np on Ns. Bingo. So that's done. I don't have anything more to add at this point, but if you have any questions, feel free, and I'll see if I can help out with some answers. But there we go. That's the detailed explanation of how transformers work and where this formula comes from.